So let's further our discussion on the inverse of A mod M. Now, if we have two numbers that are relatively prime, A and M that are relatively prime, which means that if you calculate the GCD of A and M, that will be equal to 1. And at the same time, M has to be greater than 1. Then we can say that an inverse of, then we can say when it has these two properties, then we can say that the inverse of A mod M exists. Now let's try to make sense of this. GCD of A and M is 1. Now, if you know the Bézout's theorem, it has to be of the form of S times A plus T times M, where S and T are constants. They have to be equal to 1. So basically, they both mean the same thing. Now, when we have this, then we can rewrite it in the form of congruence as S times A plus T times M is congruent to 1 mod M. 1 mod M. Now, the thing worth noting here is, in this expression of congruence, the thing worth noting is that if you look at this part in particular, T times M, and since they are constants and we assume they are integers, then we know that T times M is congruent to 0 mod M, because this is a multiple of M, so remainder will always be 0. Then this expression where we claim that this entire thing is congruent to 1 mod M doesn't make sense. This makes sense only when S of A will be S times A is congruent to 1 mod M. Now, if you look at the definition of the inverse, where we discussed that A inverse A has to be congruent to 1 mod M, then we can say that A inverse is the inverse of A mod M. So in this case, we have A and we have 1 mod M, so it is exactly the same. So what we find is that S is the inverse. So in terms of Bézout's coefficients, where we have S and T as the constant in that Bézout's theorem, T times M will be congruent to 0 mod M, so it moves out of the picture. The only thing that will give us the inverse is S times A. So S is the inverse of A mod M. Now, in order to find the inverse, the Euclidean algorithm and then the Bézout coefficient can help us in finding out the inverse. Now we'll understand that with an example. Let's try to find the inverse of 3 mod 7. Since 3 and 7, their greatest common divisor, GCD of 3 and 7 is 1. That means they are relatively prime. Then according to Euclidean algorithm, we can write this as 7. If 7, since in this case 7 is the dividend, is equal to 2 times 3. 3 is the divisor, and we'll get a remainder of 1. Now at the same time, so this is what we obtain from the Euclidean algorithm, but at the same time we know that the Bézout's equation or theorem wants us to have the representation of the form of S times A plus T times B. If this is A mod M, so in this case this is A and this is M, is equal to 1 here according to the Bézout's theorem. So this should be of the form of this equation. Now in order to make it similar, in order to make this equation which we obtain through Euclidean algorithm look like this equation, we can rearrange this equation as 7 minus 2 times 3 is equal to 1, or in other words, minus 2 times 3 plus 7 times 1 is equal to 1. So as we saw from this given equation or given expression, that 3 mod 7, here A is 3 and 7 is M is 7, so M is 7 and A is 3, then so this is A and this is M. So if you compare this entire thing with the Bézout's equation like this one, then what you obtain is S is equal to minus 2 and T is equal to 1. And we know that S gives the inverse. Therefore, minus 2 is the inverse. Minus 2 is the inverse of 3 mod 7. Now we also found in another example by doing that with another method that 5 was the inverse of 3 mod 7. Now if you look at minus 2 and add plus 7 to it, then that will become 5. And 5 satisfies that equation of the equation A inverse times A is congruent to 1 mod M. In our case, it will be A inverse times 3 is congruent to 1 mod 7. So minus 2 fulfills that criteria, 5 fulfills that criteria, and if you look at 5 plus 7, which is equal to 12, that will also fulfill this criteria. So in that case, we'll have 12 times 3 is, we have to check whether this is congruent to 1 mod 7. So for this to fulfill, for this to be, a genuine congruence, what we need to do is this part over here, this entire thing minus this should be divisible by 7. So what I mean by that is 12 times 3 minus 1 should be divisible by 7. So if you look at this, it's equal to 36 minus 1 divided by 7, and we know that that's equal to 35 by 7, and 7 will divide 35. So that's how we can obtain inverse through different methods. And here in this example we discussed Euclidean algorithm and Bézout's coefficients in particular.